Hello, my name is Aaryan Chatterjee, and this is my Falling Slinky Lab 5 in Physics 2211. Now, before we get directly into the lab, I think it's important to understand what the lab is precisely covering, which is falling objects. In real life, objects falling straight down experience the forces of gravity and air resistance, which will affect their motion. Now, in this lab, we will be focusing on analyzing an object falling down in its motion and position. More specifically, this lab will be focused on comparing an observational and computational model that considers air resistance to see how similarly or differently they describe a slinky falling straight down. Later in this presentation, we will see that both the computational model and the observational model provide similar data results at certain points, but tend to greatly differ at other points. For a preview of my lab, here's a graph that shows the predicted y position of the bottom of the slinky from the observational model and the computational model. And we can clearly see that at the beginning, both models are very similar, but then they become more inconsistent when the motion starts. However, before we go over some lab specifics, I think it's important to understand some of the crucial physics principles and ideas utilized in this lab. Firstly, it's important that everyone understands Newton's second law, which says that net force equals mass of acceleration or change in momentum or change in time. This principle helps us make the velocity update formula, which will be how we define the velocity in the computational model. Additionally, we will use the position update formula to find the position in the computational model. Finally, it's important to know that the force of gravity on an object on Earth is negative mass of acceleration, which is g, or 9.8 meters per second squared, and that the drag force equals the drag coefficient times speed of the object squared times v, which tells the direction of the air resistance. These forces will be needed in the computational models as they will affect the speed of the object. Now we must cover some major assumptions in the experiment, and one is that the object experiences only gravitational force, tension force throughout the slinky, and the drag force, and that there are no other external forces acting on it. Additionally, we assume that the object only moves in the vertical direction, and more specifically in the negative y direction. On top of the assumptions, it is important to know that the system which we will analyze is simply the slinky used in the experiment, and everything else is surroundings like the people, ground, and air. Additionally, the object's initial position is negative 0.01 meters below the origin, and that the downward direction will be the negative y direction in this case. We will analyze the slinky from t equals 0 seconds to t equals 0.516 seconds total, with the experiment starting at t equals 0 seconds, where the object has an initial velocity of 0 meters per second because it starts at rest. So, for the actual experiment, I used a video provided on campus to track the motion of the falling slinky, and this is the video that we used. And while you're watching the video, remember, it's important to know that I'm tracking the motion of the bottom of the slinky. So, when I input this video into Tracker, I analyzed the bottom of the slinky's motion by seeing where it was at different time intervals with respect to where it started, and that gave me table position points related to time, which I then put into Excel worksheet and made a graph, which I will compare the computational model to later. Now, before we get straight into the computational model, it's important to explain that we need to break the code into two different while loops. One while loop will represent the time where the bottom of the slinky stays motionless, while the other will represent the time the bottom of the slinky starts to move. So now that I explained why there's two while loops, let's get into the code. First, we need to set the initial conditions. So I set the mass to 0.22 kg, the bottom of the slinky's position to be 0.007 in the x direction, and negative 0.01 in the y direction. I then set the delta t to be 0.005 and put g to 9.8, which is the gravitational acceleration on Earth. Finally, I set the drag force constant to be 0.5 since that resulted in the best data for me. Then I start to code my first while loop, and you have to remember that the bottom of the slinky is motionless at this point, so the net force in this section should be 0. So I set the gravitational force to be mg downwards, so that means the tension force must be the equivalent of the gravitational force, but in the opposite direction. So that's what I set it to. And that results in a 0 net force, so when I update the velocity and position, nothing actually changes, making the bottom of the slinky motionless. Then in the final while loop, which represents the motion of the bottom of the slinky, I found the gravitational force and the drag force acting on the bottom of the slinky, and then I added them together to find the net force. And using the net force, I updated the velocity and position using the velocity and position update formula. After coding everything, I then ran the code, which gave me the y position of the bottom of the slinky, and I put those into an Excel chart, and then I graphed it alongside the observational data. So these are my results, and this is a graph of the computational and observational models. And the observational model is the blue points, and the computational model are the orange points. As you can see, both models accurately predicted the bottom of the slinky stays motionless at the beginning, even though the top of the slinky is let go. Unfortunately, once the motion of the bottom of the slinky starts, the two models differ greatly, as the computational model underestimates where the slinky should actually be. So the differences in the models can be explained by many different sources of error. For instance, there could have been tracker errors when calibrating the height of the slinky, making it look like the slinky traveled further than it actually did in the observational model. Additionally, the drag coefficient could have been incorrect in the code, greatly skewing our results. And finally, other forces could have acted on the bottom of the slinky, creating differences between the models. Before I end the presentation, it is important to talk about some key questions. One key question is, does the bottom of the slinky stay stationary? And the bottom of the slinky does stay stationary until the top of the slinky comes down on it. This is because the gravity force and the tension force are equal and in opposite directions, resulting in a net force of 0, making the bottom of the slinky stay at rest until the top comes down on it. Another important question is that, what if there is an object attached to the bottom of the slinky? If the slinky was still strong enough to support the object, then the same thing would happen. The bottom of the slinky and the object would stay stationary because the tension from the slinky cancels out the gravity, resulting in a net force of 0 until the top of slinky comes down to the bottom. And that's it for my presentation. Thank you for listening.